Okay, thank you everyone for showing up. I'm going to start by taking you back to like algorithm 201, right? Like we're starting to learn some fancy techniques for doing the design of like algorithms and doing their analysis as well. And you might have seen the randomized version of the sorting algorithm, quicksort, where we choose uniformly at random the pivot element. So if you see there's the uniform command that samples an element from the list uniformly at random. And you probably saw that in order to do the analysis of this thing, you have to solve the following recurrence relation, right? And if you do solve it, you'll be able to see that it's n log n versus n squared, which is what you can get if the list is in reverse order and you don't do this trick. But you're kind of like using your like computation intuitions about how to come up with this recurrence relation, right? Like if you have a very fancy language, how can you come up with such recurrence relations? So this is what I'm trying to answer in this talk, which is what is the semantic content of these kinds of recurrence relations? And of course, I'm not the first person who has tried solving these kinds of questions. We just had a talk about something very similar, right? But yeah, then like if you look beyond these kind of randomized algorithms, there's even more work, right? But like, so let's just focus a little bit on average cost. And I'm going to present two particular approaches that people have considered before. The first one uses this semantics that sees your program as a distribution over cost and output. And I'm using this fancy curly D here to mean the monad that assigns the set of distributions over a set. And you have this cost monoid here that counts how much cost has had. Something annoying about the semantics is that it's not really compositional in the sense that while you can compositionally compute the cost distribution, when you want to compute the expected cost of this distribution, you do this non-compositionally. So this is pretty bad. And it satisfies some weird equations that you don't want your semantics to validate. In particular, if you have the program that just loops forever, the semantics will say that this is equal to the program that first calls a very expensive function and then loops forever. And I'm pretty sure everyone here who has ever had to do like fancy Azure programming where these things actually cost money, you know for a fact that these things should not be the same, right? Like these are different programs. And our semantics should say that they're different. The other approach I want to talk about is the one based on the continuation passing style, where you interpret your program as an element of the continuation monad. So it's a function that receives as input a random variable and outputs a positive real number. And something bad about the semantics is that it is quite opaque in the sense that like you're just jumbling together the cost information with the randomness information into a single object. And if you want to obtain information about it, you have to probe it in very specific ways. So if you want to compute the, so like if you have this f here, that is an element of the continuation monad, if you evaluate it at the constant zero continuation, the semantics is designed in a way that you recover the expected cost. And if you evaluate it at this, the function that is only one at the event you care about, you recover the chance that this event will happen. But you have these weird things that happen in this semantics. But it suffers from the opposite issue, really, where it won't satisfy some equations that you do want to be satisfied, such as being able to reorder your programs, right? Like these kind of equations are very natural from a randomized algorithm point of view, where the order in which you sample things doesn't really matter, or shouldn't matter. So this kind of allows us to say what we want our semantics to actually satisfy. And one thing that we want our semantics to satisfy is this very nice separation between cost and probability, where we want to keep these things as separate as possible. You want it to be compositional, right, so that we can compute the expected cost of the whole program by computing the expected cost of its individual components. And you want it to be very, very close to actual probability theory, so that you can use theorems from probability theory to reason about your programs. If you look at the way these algorithms are usually reasoned about, it is very often that you need to use very sophisticated reasoning principles that should be that should be easy for you to use if you want to reason about your program. And the way we have solved this is by using this expected cost monad, where we just pair the expected cost given by a positive real number with the probability distribution on the output space. And something that I think is very, very nice about this monad is that it has a very intuitive meaning in terms of cost semantics, or rather average cost semantics. So you have the unit, which is like the operation that just outputs a value, and it should have no cost component, and it should have no randomness to it. So it just outputs 0 and the point mass distribution at the input. And if you want to sequentially compose your programs, this is how you do it. You imagine that you have a function from A that outputs the average cost of running it and the output distribution, and you want to see how to compose it with another effectful computation. And I'm not going to show the random part of this thing, because like it is not that interesting, but the cost one is quite interesting. And it just follows the idea that the cost of sequentially composing programs should be just the sum of running the input plus the sum of running the continuation given the input. But now we make things random a little bit, right? So we add the expected cost of the input. So you have this R here, which is the average cost of the input, plus the cost of the continuation, but it's average. So you have here, it's the cost, the average cost of the continuation given input A, and then you average out by the input distribution. And just to show this very simple protocol, imagine that we have this thing where we have an infinite pile of coins, and at each round, we first pick a coin, flip it. If it's tails, it's over, it stops. If it's heads, we put this coin in our pocket and then get another coin. And then we do this until until it's tails. So this is the geometric distribution, and it can be represented as this very simple functional recursive program, where let's just assume that we have an operation flip that with bias B flips a coin, and with chance B and with chance 1 minus B, right, of heads and tails. And if it's true, you add 1 to your counter, and you recursively call your program. If it's false, you just output 0. If we are to analyze this algorithm using the cost semantics we showed before, you see that you have to do a lot of very annoying algebra. So because it is a function that uses recursion, its semantics has to be some kind of fixed point. And so let's just assume that we have solved the fixed point equation, and it has given us this following distribution that is just a geometric distribution. If you are to compute the expected cost of it, we have to compute this infinite sum. And I don't know if you guys know, but this can be very annoying. And the annoying thing is that you lost the recursive structure of the program when you map it into this format, and you have to rediscover the recursive structure of your program by doing some algebra. So you see here, after doing some algebra, you're rediscovering the original expression, and now you can solve the semantics, the cost. On the other hand, if we do the expected cost semantics, the semantics itself, the fixed point equation you have to solve, is already taking care of the recursive structure of the program for you. So the semantics is just this equation, which is just very easy to solve. Like, it's just a first order equation. So like this is just one more semantics, right? Like, so you might think, okay, we already had semantics before, so why do we care about this new one? And something that I think is quite nice about this kind of work is that you can formally relate these semantics with other semantics, right? Like with the semantics I showed before. And I do this by proving the following theorem, which says that the expected cost of the cost semantics is upper bounded by the expected cost semantics. And the reason why it's not an equality is because of those weird equations I showed before. So if you restrict to the terminating fragment of your language, you do recover equality. And it gives you the same cost analysis as the continuation passing style semantics. And something else that we can say in this case is that if you look at the concrete semantics we have used, you can actually prove something even stronger, which is that our expected cost semantics in the category of quasi-Borel spaces with order, the expected cost monad is exactly the affine fragment of the continuation monad. And of course, I mean affine in the algebraic sense, not in the PL sense, though they are very much related. But it just means that the continuation can be written as a sum of a constant plus a linear operator. So like the idea being that it's the cost plus the probabilistic aspect of the semantics. Yeah. And if you go on the paper, there's a bunch of other stuff we have done. I just want to focus on the first two, which showcases why we need to use these fancy quasi-Borel spaces, because we have high-order functions, we have continuous distributions, and we have recursion. So we need sophisticated semantic domains. And just a parting thought is that even though the semantics I've used is quite concrete, the idea of this expected cost monad is very general. So if you have other kinds of applications where you want to reason about average cost of your program, but you have a different semantic domain, you'll most likely be able to adapt the monad to your application. Yeah, this is all I have to say today. Thank you.
Questions?
Hi, the talk was great. Thanks for that.
Thank you.
I was wondering if in the process of applying these semantics to get expected cost for some of the programs, that you run into any interesting inference problems where the semantic led to some algebraic form that you needed to solve using probabilistic inference.
Yeah, for sure. Like, even though I showed the expression you get, like there is some, there's one simplification here that you have to do, which is to use the fact that your program terminates with probability 1. So like these are the kinds of things you have to think about when doing the analysis.
Right.
And kind of show it, yeah.
Okay. I would be happy to talk offline more.
Yeah, for sure.